morning, class. Hope you've been well. Now today we are going to look at computer systems. Specifically, we are going to look at the hardware. If you remember, in our last lesson we discussed about introduction to the computer system. We discussed about the history of computers. We also discussed the types of computer systems. So today we are going to move further and look at the computer hardware. Basically, a computer hardware are physical parts such as the system unit and the peripheral devices. The system unit refers to that box, the box that houses the hardware systems inside, the wires, the ports, among others. And the peripheral devices refers to things outside that box, in quotes. These are the input devices as well as the output devices. Now, the peripheral devices connect to the system unit, what we are referring to that box. The system unit include or has the following peripheral devices. Number one, it connects to the input devices. It connects to the central processing unit. It connects to the output devices, and it connects to the storage devices. Now, what are these input or output devices that connects to the system unit? Now, the input-output devices are usually external to the computer system. Now, looking at the first group, the input text input devices. These are the devices that help the user to input text into the computer system. Number one, we have the keyboard. This is a device that's used to input text as well as characters. This is done by pressing the buttons, and these buttons are sometimes referred to as keys. These keys usually are similar to a typewriter, for those who are old enough to have seen the typewriters. The next group is the pointing devices. These are still input devices, but under the category of pointing devices. So number one, we have the mouse, which is a pointing device that detects two-dimensional motion relative to its supporting surface. It's used to point at objects on the screen. The next one, we have a trackball. This is also a pointing device which consists of an exposed protruding ball which is housed in a socket that can detect rotation about 2 axes. We have another type of input device known as Xbox 360 controller, which is used for the switchblade application. It can be used also as an additional pointing device with the left or right thumbstick. We also have another group known as gaming devices. For example, a joystick. This is a general control device that is made up of a handheld stick that looks like a vehicle gear stick that pivots around one end and can detect angles in 2 or 3 dimensions. We have another gaming device known as gamepad. This is a general game controller which is held in the hand and which always relies on the digits that provide input. Another category of input device is the image and video input devices. For example, we have an image scanner. This is a device that provides input by analyzing or processing images, printed text, handwriting, or an object and takes it into the CPU for processing. Another example is the webcam. This is a low-resolution video camera used to provide visual input that can be easily transferred over the internet. Some of these webcams are inbuilt, while some are external. Moving to the next group of input device, we have the audio input devices. A good example of an audio input device is the microphone. It's an acoustic sensor that can provide input by converting sound signals into electrical signals. Parts like the motherboard, expansion cards, and modems. Many hardware devices can be attached to a system unit to expand its capabilities, such as a speaker, a scanner, or a printer. This attachment is provided for by the use of ports. These are openings such as USB port that can be used to attach these devices into the system unit. So that's computer architecture. We've looked at the system unit and the hardware that are found inside it, plus the peripherals. Now, a computer design involves creating and building the computer itself. This includes developing the hardware structure, selecting the system components, that is the input system, input subsystem, output subsystems, the motherboards, among others, and assembling them so as to function as a complete system. Remember, a system refers to as a set of interrelated components that work together towards a common goal. Therefore, these components could be the hardware components, the software components, the people using them, among others. So let's move into the first component, a very important component within the system unit. This is called the Central Processing Unit. The Central Processing Unit, CPU in short. Now, the components of the CPU include the arithmetic and logic unit, ALU. This is responsible for performing all arithmetic as well as logical operations. Arithmetic operations include addition, subtraction, multiplication, as well as division, while logical operation include AND, OR, and NOT. The other component of the CPU is the control unit, known as the CU. This CU manages the execution of instructions by way of directing the operations of the arithmetic and logic unit, the memory, as well as the input and output devices. So it manages the instructions, it manages the operations, it manages the relationships between the ALU, the memory, and the input/output devices. It retrieves instructions from memory, for example, decodes them, and signals the required component to execute or to do a given task. The last component of the CPU are the registers. This refers to small and fast storage areas within the CPU that holds data, instructions, and addresses temporarily. There are different types of registers. For example, we have the accumulator, which stores immediate results of operations. We have the program counter, which is also a register that holds the addresses of the next instruction to be executed, and also instruction register, which stores the current instructions being executed. Now, the functions of these components include, number one, the ALU. This performs all mathematical calculations and logical decisions. It receives input from the registers, then processes them and stores the result back in the registers. Remember, we had different types of registers. That is the accumulator, the program counter, and the instruction register. second function, so the second component, that is the CU function. The CU orchestrates the execution of instructions by controlling the flow of data between the CPU, which is the brain of the computer, the memory, which stores data and information temporarily or permanently, and the peripherals. Remember, the peripherals are the devices found outside the system unit. The CU ensures that instructions that are fetched, decoded, and executed or processed are in the correct sequence. That's why it's called a control unit. Then the functions of the registers. These serve as the CPU's internal memory, which temporarily holds data and instructions that are being actively used in the processing. Therefore, they help in speeding up the overall performance of the computer system. Now let's look at the instruction set. An instruction set basically is a collection of machine codes that a computer central processing unit is designed to understand and process or execute. It's basically a set of instructions that the CPU is designed to understand and process. There are some. It's an example of maybe we could say a guideline that helps the CPU to execute the processes. Each instruction in the set tells the CPU to perform a specific operation. For example, adding, subtracting, dividing, etc. It also tells the CPU to perform an instruction such as data transfer or control operations. Now, there's something called the ISA, that is the instruction set architecture, which defines the capabilities of the processor in terms of the operation it can perform. Now, what's the importance of the instruction set? Number one, the instruction set defines how the CPU will interact with the memory, how the CPU will interact with the input and output devices, and also how the CPU will interact with the other parts of the computer system. Another importance of the instruction set is that the complexity and efficiency of the instruction set can affect the performance of the CPU, and therefore it can influence how fast a program runs. So if the instruction set are well coordinated, are well written, the efficiency and performance of the computer system will be improved. The efficiency and performance of that system will be high, as opposed to a poorly written instruction set which may slow down the performance and efficiency of the computer system. Now let us look at the instruction cycle. The instruction cycle is the process in which a computer's CPU retrieves, which means it pulls in, it gets, the process by which the CPU interprets, meaning it gives meaning, and executes, processes, that is, instructions from the memory. So the CPU retrieves information from the memory, most cases from the primary memory, and then interprets and processes the instructions. So it is a cycle: retrieving, interpreting, executing, and storing. There are 4 steps: retrieving data, interpreting data, executing data, and storing data. Let's look at the first step, the retrieving or fetching. The CPU retrieves or fetches the instruction from the memory. This memory, like I've said, is the primary memory, usually the random access memory or RAM. The program counter holds the address of the next instruction to be executed, and the instruction is fetched from memory and loaded into the instruction register. After fetching, the program counter is incremented to point to the next instruction in the memory. The second step in the instruction cycle is decoding. In this step, the CPU interprets or decodes, meaning it gives meaning to the fetched instruction. The control unit decodes the instruction to understand what action is required. Is it addition? Is it subtraction? Is it a logic instruction? So the control unit decodes that instruction to understand what action is required. The instruction typically includes an opcode or operation code that specifies the operation, and I'll give an example: addition, subtraction, data load, etc. The decode process also identifies whether additional operands need to be fetched from memory or register. The third step of the instruction cycle is execution. In this case, the CPU performs the operation specified by that instruction. This depends on the instruction type, which may be an instruction to perform arithmetic or logic operation using the ALU. It could be an instruction for reading from or writing to memory. It could be an instruction for transferring data between the different registers, or it could be instruction to change the flow of the control. Now the execution involves accessing registers, memory locations, or performing calculations. The fourth step is storage. That is, if the instruction generates a result, if the process produces a result, this step stores the result in the appropriate destination. The destination may be a register or even a memory location like RAM. For example, after an arithmetic operation, the result may be stored in the accumulator or a general purpose register. After that, the CPU moves on to the next instruction in the cycle. Now, let's look at the different types of instructions which can be handled by the CPU during its operations. We have different categories of instructions, that is, memory access instructions, arithmetic instructions, logical instructions, and control instructions. Let us look at the first one, memory access instructions. These instructions deal with moving data between the CPU and the memory. That's why it's called memory access instructions. The instructions that relate to the movement of data between the central processing unit and the memory. For example, load is an instruction which transfers data from memory to a register. We have another example, store. This instructions writes data from a register to memory. Remember, memory is a storage area in a computer system. We have another example, move. This transfers data from one register to another. The purpose of this instruction is to retrieve or to store data required for processing. The second type of instruction is the arithmetic instructions. These instructions perform the basic mathematical operations, which include add, subtract, multiply, divide. Add adds two numbers. Subtracts one number from another. Multiplies two numbers. Divides one number by the other. The purpose of arithmetic instruction is to do or to perform mathematical calculations on numeric data. The third type of instruction is the logical instructions. The logic instructions perform logical operations, for example, comparing, as well as the manipulation of bits. Examples include AND, which performs a bitwise AND between two operands. For example, A and B. We have the OR logic instructions, which performs a bitwise OR between two operands. For example, 1 or 2. We have the third one, NOT, which inverts the bits of a given operand. For example, NOT A, NOT B, etc. Then we have XOR, which performs an exclusive OR between two operands. And finally, compare logic instructions, which compares two values and set flags based on the result. The purpose of this logic instruction is to manipulate bit or test conditions. Then we have control instructions, whose purpose is to control the flow of program. Now, these control instructions alter the normal sequence of execution. For example, we have jump, which changes the flow of execution to a different memory address. We have call, which calls a subroutine or calls a function. We have return, which returns from a subroutine to the calling function, and branch, which is based on the outcome of a comparison or a condition. Now let's look at storage devices, which are part of the computer hardware. Now we look at the memory unit. This is a crucial component of a computer system, which is responsible for storing and retrieving data and instructions that are used by the central processing unit. This unit holds information, either temporarily or permanently, and this depends on the type of memory. This is because we have two types of computer memory: the primary memory and the secondary memory. The primary memory, which is also referred to as the main memory, is a volatile memory. This means that the data which it holds gets lost when the computer is turned off or when the power goes off. For example, random access memory and cache memory are all primary memories. The functions of a primary memory is to hold data temporarily while instructions are currently being used by the CPU. It also provides fast access to data. This enables the CPU to process data efficiently. The characteristics of the primary memory include fast and direct access by the CPU, but the limitation is that the storage capacity as compared to secondary memory is very limited or is very small, meaning it cannot hold large data. Now, looking at the secondary memory, this is a non-volatile memory, meaning that data can be retained even when the computer is powered off. It can keep data even when there is no power. Examples include the hard drives, the solid-state drives, CDs, DVDs, and USB flash drives. The functions include to store data that are not currently being in use but may be needed in future. It's also used for long-term data storage. Then you have the cache memory. This is a small, high-speed memory which is located close to the CPU. It's used to temporarily store data that is frequently accessed by the CPU. The CPU first checks the cache for the needed data, which significantly speeds up data retrieval as compared to accessing it from slower memory sources. Now, looking at the memory size, the computer memory is measured in units such as bytes, with common larger units which include a kilobyte, which is roughly 1,000 bytes. Remember, a byte has 8 bits. 8 bits, which could be zeros and ones with different patterns. We have a megabyte, which is 1024. We have gigabytes, which is 1000 roughly megabytes, and we have terabytes, which is roughly 1000 gigabytes. Now, computer organization deals with how operational attributes are linked together and contribute to the system architecture. It usually focuses more on the implementation and efficiency which covers hardware details like control signals, peripherals, memory types, among others. Now let's look at the interconnecting units of a computer system. We have something known as a bus. Now, a bus in a computer architecture is a communication system that helps in the transfer of data between one component inside or outside of a computer system. Basically, these are pathways. You could call them roads, pathways, through which data flows between the different parts of a computer system. This could be a bus between a CPU and a memory, a path between input and output devices, etc. Basically, a bus is a collection of wires or connections or circuits that carry data, that carry addresses and signals between the different hardware components. It helps in ensuring that the CPU can communicate with the memory, the CPU can communicate with the peripherals, and the CPU can communicate with other computer components. We have both internal and external buses, where the internal bus is also called a system bus because it is internal. This bus is found within the computer's motherboard, and it connects internal components. For example, the CPU, the memory, and other core system components. External bus is known as an expansion bus. This connects the internal components of the computer to external devices, also known as peripherals. For example, it connects the internal components to printers, to external drivers, or other input-output components like speakers, etc. This type of bus allows data to be transferred to and from devices outside the core system. For example, we have the USB, which is the Universal Serial Bus, the Universal Serial Pathway. We have the PCI, which is known as the Peripheral Component Interconnect Bus, as well as the Thunderbolt bus. A computer bus basically consists of three primary components or sub-buses within a specific function. We have a data bus or a data pathway, which is responsible for carrying actual data that is being transferred between the CPU, memory, and other components. This bus is bidirectional. This means that it can flow both ways, from the CPU to memory and vice versa. We have the address bus, which carries memory addresses or locations where data is either read from or written to. Now, this bus is unidirectional. This means that it can only go one way. For example, from the CPU to the memory, or from the CPU to the input-output devices, or from the memory to the input-output devices. Then we have the third type of bus, known as the control bus, which carries control signals from the CPU to other components in order to coordinate the operations of the computer system. This control bus is responsible for signals, for example, read, write signals, interrupt request signals, among others. Now let's look at the common expansion bus technologies. Remember, expansion bus connects the external devices to the system unit components. Number one, we have the peripheral computer interconnect. It's a technology which is a standard for connecting peripheral devices to the motherboard. It is a parallel bus architecture. This allows the CPU to communicate with devices, e.g. the sound cards, network cards, and storage controllers. The second common expansion bus technology is the AGP. This is the accelerated graphics port. This is the specialized expansion bus which is designed to specifically handle graphic cards. The key feature is that it offers a faster data transfer rate than PCI for graphics. Then we have the USB. This is a widely used expansion bus standard for connecting a wide range of peripherals, including the keyboards, mouse, printers, webcams, etc. It is specifically designed for both data transfer and power supply. Now, the performance of the computer, we're going to look at the factors affecting the computer performance. The major ones are the registers. That means that the size and number of registers affect how much data the CPU can process at a time. Meaning, the larger the registers, the faster the speed of the computer. Another factor that determines the performance of a computer is the random access memory, which is used to store data and programs which are currently being used by the CPU. More RAM allows the computer to handle more processes simultaneously, and hence reducing the need for the system to swap data in and out of slower secondary storage devices. The other factor is the system clock. That's the clock speed. This means that the higher clock speeds, measured in megahertz or gigahertz, allows the CPU to process more instructions per second. Then we have the system bus. This means that the system bus width, if it's higher, it will allow for more data to be transferred in a single operation, as opposed to a smaller or narrower system bus width. Now the bus speed, which is also measured in megahertz or gigahertz, also affects how quickly data can be transferred. Then the other factor is the cache memory, meaning that the larger the cache and the faster the cache memory, the reduction in the time the CPU spends waiting for data to be fetched from the RAM, and this significantly improves the performance. So the systems with larger cache sizes usually perform better than systems with smaller. Now looking at the components inside a computer cabinet, this box. Now the inside, when you look at the inside of a computer cabinet, which is also known as the system unit or case, houses several components that work together. Number one is the motherboard. This is the main circuit board that connects to all the other components of the computer. We have the power supply unit, which converts electricity from the wall socket into the type of power the components inside the computer need, that is direct, the DC, direct current. So it distributes power to all components in the system: the motherboard, storage devices, expansion cards, etc. Now inside the computer cabinet we also have the memory. That's the random access memory, which we had said it's a temporary memory that the system uses to store data that are currently being processed by the CPU. Then we have the expansion slots. These are slots which increase the capabilities of the computer by allowing upgrades or additional functionalities. We have the processor itself, the CPU. This is the brain of the computer, responsible for executing instructions and performing calculations. And we have the cables, which connects the internal components to deliver power and data. We also have inside the computer component the storage devices, that is the hard disk drives or the solid state drives. We have optical drives, etc. So that's the end of our lesson today. And remember, your computer is a tool and not a master. Use it wisely and it will serve you well. Thank you very much. Let's meet in the next lesson.